Okay, it started. Okay, so good morning to everybody. Welcome to this sixth seminar within the Use Colloquia. Today we have the pleasure to have a speaker, Mr. Mattia Bianchi. Thank you, Mattia, for accepting to be here with us today. Let me spend a few words about Mattia first. So Mattia is actually a PhD candidate in the Delft Center for Systems and Control in TU Delft, the Netherlands. He received the bachelor and master degree here in L'Aquila, respectively in 2016 and 2018. In 2018, he visited the Control Systems Technology Group in Eindhoven. Then in 2021, 2022, he visited the Mechanical and Aerospace Engineering Department at the University of California at San Diego in the United States of America. So his major studies, his major research interests are within the game theory and operator theory to solve decision and control problems for complex systems. We are very happy because I already said that Mattia was a former student of us, and in 2021 he was the recipient of this very prestigious award, that is the Roberto Tempo Best Paper Award at the IEEE Conference on Decision and Control. So thanks again for being with us today, Mattia. So you can please share the screen.
Oh, not sharing the screen?
Not yet. Okay.
Okay. Thank you, Professor Fora, for the kind introduction and for the invitation. I see many of my former professors in the participants. I'm very happy that I can give this presentation. I hope that next time it will be in person. And yeah, my talk is about generalized Nash equilibrium problems over networks. I'm working with this on this topic with my supervisor at TU Delft. Oops, sorry. Sergio Grammatico, and I also want to thank Giuseppe Belgioioso, which is co-author of most of the work I'm going to present today. So to start, let me explain why we study games. Games are used to model the interconnection, the relation between interdependent agents, which are self-interested. In this example, in this picture, there is a very famous traffic jam, actually a massive traffic jam that happened in 2010 in China on the highway 110. And there was no apparent reason for it. And it was since then a very well studied phenomenon. And it represents what can happen when self-interested agents take decisions without any form of control, without any form of regulation. And in this scenario, the agents are the drivers. Each driver chooses the route that minimizes the time spent on the road. And the problem is that this time also depends on the decisions of the other drivers. And why we study games? We study games mainly for two purposes. One is modeling. So when we want to predict the outcome of the complex interaction between agents, selfish agents. But when we are only modeling, we cannot control the outcome, and then disasters can happen, like in this massive jump. And the other objective, which we are mostly interested in, is regulation, namely the design of mechanisms and behavioral rules or incentives for the agents to obtain a desirable equilibrium. So let's start by formally defining a game. What is a game? It's composed of a set of agents we call calligraphic I of n agents. And each agent has a decision variable, which we call xi, which belongs to a feasible set omega I. And this feasible set can be either a discrete set, or it can be a subset of R and I. So we are either talking about a discrete game or a continuous game. And in particular, since I'm always receive this question, the second case, so the continuous case, also contains the case of mixed strategies, where the decision variable xi is actually a probability distribution over a number of possible choices. And then each agent has a cost function that wishes to minimize. And this cost function depends on both on the action, on the decision xi, on the strategy of the agent I, but also on the strategies of all the other agents. And this is where the interconnection between the agents arises, because they are coupled through their costs. And what we call a game is indeed a set of interdependent optimization problems, where the problem of agent I is parametric in the strategy, in the actions of the other agents x minus I. And just to make an example of a game, games were historically studied to model the competition in markets. So they were initially studied in economics. And in this picture, I made an example of an electric market where the agents are producers. And their decision xi is the quantity of energy to produce. And they do so with the only aim of maximizing their profit and not caring about the welfare of the other companies, of the other agents. The complication arises because the profit of each company does not depend only on the decision, but also on the decision of the other producers. For example, because, well, there must be a cost to produce the energy, which is dependent on the quantity of energy produced. And then the company tries to maximize the revenue, which is given by a certain price, which, however, depends on the action of all the agents, for example, because of price elasticity. So this is a very simple example of games, and in economics you can find as many as you want, for example, auctions or Cournot competition. Okay, now we have this mathematical object, which is a game, and we define a solution concept. And I will only deal with one solution concept, which is the probably most used and most useful, which is the Nash equilibrium. But it's not the only one. Even the utility of the Nash equilibrium was discussed for a long time, and there are so many other concepts like Pareto optimality, or even different types of games like repeated games or sequential games, which we will not deal with. But we'll just deal with the Nash equilibrium problem. So on top you see our game, the set of interconnected optimization problems, and a strategy X star that is a solution for each optimization problem is a Nash equilibrium. This means that at a Nash equilibrium, no agent can unilaterally change its strategy to improve its costs. And not once again that this minimization problem is parametric in the action of the other agents. And the one on the right is John Nash, who had schizophrenia and a lot of imaginary friends. I recommend watching the movie A Beautiful Mind in case you missed it. So okay, our solution concept is the Nash equilibrium. And why do we think that this equilibrium is in some way desirable, is a desirable outcome for a game. Well, indeed, Nash equilibrium problems can be used in many engineering applications. For example, one use is for regulating competition and with the so-called mechanism of or incentive design. In the picture, there are some plug-in electric vehicles depicted, and indeed each user of an electric vehicle is an agent, and its only aim is to charge his car with the least cost possible and in the least time possible. How can a designer improve the performance of the electric grid? How can a system operator incentivize a correct use of the electric grid by the drivers of electric cars? This can be done, for example, by changing the price of electric energy to push most of the drivers to charge their car at night, for example, where the demand for electric energy is lesser. And the choice of incentives to push the agent toward a desired equilibrium is called mechanism design. And although Nash equilibria are usually connected with competition, Nash equilibrium problems also arise in a lot of cooperative problems. And when you have to ensure cooperation among the agents in a network. One famous example is the case of distributed optimization, which was reformulated throughout the years by different authors as a Nash equilibrium problem. And what's the advantage of reformulating a distributed optimization problem as a Nash equilibrium problem, where you can enhance robustness, for example, if one of the agents fails. And as a particular example here, I chose a very famous one, which is the positioning of mobile sensor networks. So each agent is its own sensor with the sensing capacities, and each agent sensor is equipped with a cost function, which depends not only on its position, but also on the displacement with respect to the other sensors. And aside from that, Nash equilibrium problems arise also in a variety of computational problems. For example, GANs in machine learning, or model fitting, or in the problem of constraint consensus in signal recovery. More in general, in any saddle point problem can be formulated as a Nash equilibrium. So either we are seeking cooperation over a network, or we are trying to regulate the competition among selfish agents. What we need mathematically are algorithms for seeking Nash equilibria, algorithms for finding Nash equilibria, possibly distributed algorithms. And this is particularly important in the case of a big number of agents and a lot of data. For example, distributed and parallel computation infrastructure are already kind of widespread in many learning algorithms, where not all the data can be kept in one single place. This would be too expensive. So yeah, that's what my research and our research at Delft is mostly about. We study efficient distributed Nash equilibrium seeking algorithms. Okay, this was just the motivation. I will now go to a more technical part. Please feel free to interrupt me at any point for questions. And okay, so how do you design a Nash equilibrium seeking algorithm? Well, there are different ways, of course, but one that we particularly like is to use operator theory for Nash equilibrium seeking algorithms. And this is how we do it. So first of all, sorry for that. So we restrict our attention to continuous and convex games in the sense that the feasible sets are a subset of R and I, and convex in the sense that gamma is omega is closed and convex set. And we will also assume that the cost functions with respect to the first argument, so with respect to the on action of agent I, are convex and continuously differentiable. This can be somewhat relaxed, but for simplicity, I'll take these assumptions throughout the presentation. And so we call this game a convex game. So because now each optimization problem of the single agent is a convex optimization problem, we can reformulate the problem of finding a Nash equilibrium as a monotone inclusion, an inclusion problem, where this F is an important operator, which is the pseudo gradient mapping that basically collects the stacked gradients of the cost function of each agent, but only with respect to the local strategy, the local variable xi. And okay, this mapping is not a gradient. And this other part instead is the normal cone of the feasible set omega. Which is basically the subdifferential of the indicator function of the set. And if you're not very familiar with the concept of subdifferential of subgradient, just assume that this normal cone is 0, which will correspond to the case of gamma being the whole space Rn, and where n is the dimension of x, and x is, I recall, the stacked vector of all the strategies. So this condition in the box is just the first order optimality condition for each of the optimization problem of each agent stacked together. And this is an inclusion problem, so the problem of finding the 0 of an operator. And why did I already mention twice a monotone? Because we will assume as our weakest assumption that the pseudo gradient mapping is monotone, which means that this inequality holds for all x and y in Rn. And sometimes we will instead require a stronger assumption, which is strong monotonicity, which means that this holds for some mu bigger than 0. And monotonicity plays in game the same role that convexity has in optimization. In fact, whenever f is the gradient of a function, which is not usually the case for games, and f is convex, then delta f is monotone. And similarly, delta f is strongly monotone if and only if f is strongly convex. And although f is not a gradient, the fact that we are assuming that f is monotone implies by itself that the cost functions are convex with respect to their first argument for each x minus I. Okay. So this is our first working assumption, and that's why we call our inclusion a monotone inclusion, because the first operator is monotone by assumption, and the second one is monotone by convexity properties. So what's the idea? Why did we reformulate the Nash equilibrium as a monotone inclusion? We did this because now we have a systematic way of deriving algorithms exploiting operator theory, exploiting monotone operator theory. In particular, we start from our game, which outcome we don't know. So if we let the agent free to, for example, perform their best response to the other's agent, we don't know if the game is going to converge to a desirable equilibrium. Instead, we reformulate the problem of finding a Nash equilibrium as a monotone inclusion. And then we solve this monotone inclusion using tools, fixed point iteration, which are well developed in the literature. And this ensures that the strategy of the agents will eventually reach a desirable equilibrium, which is, in our view, a Nash equilibrium. So as a simple example, let's solve this monotone inclusion. We can use an algorithm which is called forward backward algorithm, in which this part is the part which deals with the constraints, which we will not look at too much. And this part, where tau is a step size, resembles the gradient method, except that f is not a gradient. And in fact, if you write this for each agent, you get this iteration, which is exactly each agent performing a projected gradient step with respect to its cost function, parametric in the cost functions, in the actions of the other agents. And it's kind of expected that when f is strongly monotone and Lipschitz, the algorithm converges with the linear convergence rate. So this forward backward algorithm, where this part is called backward and this part is called forward, is just one of the techniques that we can use to solve a monotone inclusion problem. And as a result, we get a Nash equilibrium seeking algorithm, which is distributed. And we say distributed because the computation is shared among the different agents, although each agent, to perform this update, agent I needs to know all the actions of all the other agents at time x minus I. We are instead interested in a more distributed setup, which we call fully distributed. So the idea is that when there is no central coordinator, it's very difficult for agent I to access the decision of the other agents. So x minus I is not known, and agent I cannot use it to update its strategy. This situation arises, for example, in the sensor network application that I described before, or for whenever there are ad hoc networks. So because agent I does not know the action of the competitors, agent I tries to estimate it. And in particular, each agent keeps an estimate of the action of the strategy of each other agent. And we denote by this xij, the estimate kept by agent I of the action xj. And then the user assumption is that sorry about that. Okay. The user assumption is that the agents will exchange their strategy on an undirected and connected graph. And this assumption was, for example, used in many papers in the literature. So now I talked about an operator theoretic approach to design Nash equilibrium seeking algorithms. I talked about partial decision information scenarios about fully distributed algorithms. And now I want to know if I can use operator theory to solve the games in the partial decision information scenario. And the answer is yes. I can actually reformulate the Nash equilibrium problem under partial decision information as a monotone inclusion, or at least as an inclusion. So this is the first case we have seen. where I remove the part related to the constraints for simplicity of notation. And now we can prove a different inclusion, so that a point is a Nash equilibrium if and only if this strategy, which is the estimate of which represent the estimate of all the agents, but at consensus at the Nash equilibrium. So X star is the estimate, is an estimate of all the agents when all the agents reach consensus on the solution. So a point is a solution in this extended space of estimates, if and only if, sorry, it's supposed to be X star. Sorry about that. If and only if it is at 0 in an augmented operator, FA, which is defined by this sum, where on the right you just have the Laplacian of the undirected and connected graph, Kronecker, an identity matrix, and on the left you have the extended pseudo-gradient mapping, which will be the gradient mapping, the pseudo-gradient mapping, but computed on the estimate. So each agent is not computing the gradient of its cost function on the real strategy of the other agents, but on an estimate. And this matrix R, it's just for the dimensional compatibility, so it adds some 0 to this mapping, which is not an operator, because the estimates belong to an augmented space, which is n times bigger than the real action, which belongs to Rn. So we can reformulate the Nash equilibrium problem under partial decision information as an inclusion. In particular, note that this part enforces the consensus of the estimate. So when this part is 0, the estimate must be at consensus for some strategy, and this part forces optimality in the sense of the Nash equilibrium. So it's also important to note that when the estimates are at consensus, the extended gradient mapping and the pseudo-gradient mapping are the same, they coincide. However, an important limitation is that this operator is not monotone. Actually, you can prove that this is never monotone. It's without. The inclusion that we defined is not a monotone inclusion in general. And in fact, if F is only monotone, the Nash equilibrium problem under partial information is still an operator problem. Instead, if we assume something stronger on F, we can retrieve derive some convergent algorithms. In particular, if we assume that F is strongly monotone and Lipschitz, for a small enough alpha, where alpha is the step size in the definition of the augmented operator, then we can prove that F is restricted strongly monotone, where restricted means just with respect to the solution. And this is enough to derive some algorithms. For example, if we apply once again the forward-backward algorithm to the operator FA, so to this augmented operator in this augmented space of the estimates, we get this algorithm, which is a projected gradient algorithm. And okay, this is agent I is updating the estimates of the others. Of the other agents. Simply according to a consensus protocol. So the estimates are updated according to a consensus protocol, and the real action is updated according to a projected gradient step plus some consensus terms. So basically how does this work is that in a very natural way, you have a combination of consensus and pseudo-gradient dynamics. And these algorithms are very well developed in literature. However, they have some limitation because the restricted strong monotonicity constant of the operator Fa is usually very small. And most importantly, it decreases with when the number of agents increases. So this means for our algorithm that the step sizes that guarantee convergence are very small because they are proportional to the strong monotonicity constant. In particular, in the application I've seen, they can easily reach 10 to the minus 9, which is not reasonable. And because of that, the algorithms are very slow. And in particular, notice that each iteration of this algorithm require each agent to exchange the estimates of all the action, the overall action, with all of its neighbors. So it's not only slow in terms of communication, it also means that it's very inefficient from an energetic point of view because the agents have to communicate a lot of data. And finally, the convergence rate depends quadratically on this small constant mu. So to solve this problem, we will propose a different algorithm, which is a preconditioned proximal point algorithm, for short PPP. First of all, a little bit of background on the proximal point algorithm. Assume that you want to find the zero of an operator calligraphic A. So you want to find this point omega star that makes A 0. So this is the proximal point algorithm, where this -1 denotes the inverse operator and ID is the identity operator. And this, it's not very clear how to implement this algorithm, but indeed what this tells you, it's an implicit method where you have to choose the next iterate as the solution of this inclusion. So basically, at each iteration of this algorithm, you solve a regularized inclusion that still contains the operator calligraphic A. And tau is up step size, and in particular, this algorithm converges for any tau bigger than 0 without any restriction. So, for example, if A is the gradient of a convex function, then the proximal point algorithm it's simply this iteration, but at each iteration, to minimize the convex function f, which is what you are doing by imposing delft f equal to 0, you have to solve a regularized optimization problem. The good thing is that if you are able to apply these two games, the step sizes will not depend on you. And so we can get much faster convergence and much bigger step sizes. So we have said that seeking a Nash equilibrium in a partial information scenario means finding at 0 of the operator augmented Fa. What happens if we just apply the proximal point algorithm to this operator Fa? Two things can go wrong. The first one is that Fa in general is not monotone, it's just restricted monotone. I recall that Fa had a part with the extended pseudo gradient and a part which had the Laplacian. And this part is not monotone. So the first thing that can go wrong is that Fa is only restricted monotone, but we can solve this. In particular, we showed that the proximal point converges under mild assumptions also, even if the operator is only restricted monotone. And the second more fundamental thing is that this algorithm is not distributed. So this iteration cannot be computed in a distributed way. And to see why, you just have to note that if we want to perform this algorithm, we have to, at each iteration, to solve an inclusion where part of the inclusion has fxk plus 1. And because fa contains the Laplacian, this means that the update of agent I also depends on the next iterate of agent J. This means that the algorithm is not causal, and in particular, it cannot be implemented in a distributed way. It will require at each iteration to solve a game and to perform infinite communications among the agents. And this is a well-known fact even for the case of full information, so where the agents know the strategies of the other, that the proximal point algorithm cannot be implemented in a distributed way. However, we have a solution for this, which is a technique called preconditioning. Instead of seeking a zero of this operator fa, we want to seek a zero of this operator preconditioned with the preconditioning matrix phi, which is positive definite. And of course, the zeros of fa coincide with the zeros of phi minus 1 fa, because the matrix is invertible. And this technique was also used in a different context, but in games under partial decision information. So this is our new algorithm, where we have to choose appropriately this matrix phi. In particular, if we choose it as 2 identity minus L, where L is the Laplacian of the graph, we get an algorithm which is fully distributed. And we can even show this. So if we bring the inverse operator on the other side, we get this equation by multiplying everything by phi. We obtain this. So now we have where now this this fa of xk plus 1 contains so the parts that depends on the Laplacian on the graph and on the other agents, the lakes, and you can compute this iteration in a distributed way. And in particular, the algorithm that you obtain when you do all the computation looks like this, where it has a consensus of the estimates. So the estimates are still updated according to a normal consensus protocol, where these are the weights of the graph. And the on action of the agents is updated according to a proximal best response, where you have a best response with respect to the cost and the updated estimates. Then you have a damping term, which is normal, and you have a consensus part. But what is important that this iteration does not depend on anything which is of agent J and of at time k plus 1. So it can be implemented in a totally distributed way. And in particular, each agent only is required to solve an optimization problem of small dimension at each iteration. So why does this converge? The idea is that even if fa, this operator, the preconditioned operator, is not monotone, however, it can be shown to be monotone in a weighted space, where the weighted space would be the one defined by this weighted inner product. Then we apply the proximal point to this space, and we get a result that says that if f is strongly monotone and Lipschitz, if the graph is connected and directed, and if the one step size is chosen small enough. Notice that we don't have the second step size we had in the forward backward anymore. Then we achieve linear convergence. And what are the advantages with respect to forward backward methods? So first of all, the step size in the forward backward methods go to 0 when the number of agents increases, while the only step size in our PPP is independent of the number of agents. And the other thing is that the convergence rate, instead of depending quadratically in that very small parameter mu, depends on mu linearly. And okay, this is some numerical results on a mobile sensor network Nash equilibrium problem, which shows that in effect the algorithm outperforms the gradient methods. And you might think that this is natural because different from the gradient methods, in this algorithm, we are requiring each agent to solve an optimization problem at each step. So we are trading efficiency in terms of a number of iterations with the fact that the update is more expensive. But why is this convenient in a distributed setting? This is because although the local computation increases, the communication decreases by a lot. And okay, then because we took an operator theoretic approach, we are also able to easily generalize these results, because I mean the algorithm is very simple, and you could deduce the linear convergence of that algorithm even for without using operator theory. But what operator theory really does, it gives you a systematic way of exploiting modularity, so that if you consider a different or more complex problem, or you add some terms like we will do now, the convergence proof is not remarkably difficult, and instead you can use a set of tools which are already developed. So in particular, the first extension we consider is for generalized games, where there are coupling constraints that among the agents. So the agents are not only coupled through their cost, but also via their feasibility sets. And we define the generalized Nash equilibrium as a solution of this generalized game. And yeah, generalized games arise everywhere where agents are competing for resources, for example. And I mean, the coupling constraints are actually arise quite naturally in almost all games. And we can reformulate the problem of finding generalized Nash equilibrium using duality. So we are using the KKT conditions for each one of these optimization problems. We can write some KKT conditions. In particular, we will I will go fast on this and skip this part, but we will only focus on a particular type of equilibria, which have the same dual multipliers for all agents, which are called variational. They are more easy to compute, but they are also more fair from an economical point of view. They correspond to a situation which does not discriminate between the agents. But what we are interested in at the end of the day is that you can reformulate the problem of finding generalized Nash equilibrium, indeed a variational generalized Nash equilibrium, as the problem of finding a zero of a certain operator. And now this operator is much more complex with respect to the case of a non-generalized game. We have to augment the state with dual variables and some lambda and some auxiliary variables z. But the idea is the same. Now that you have reformulated the GN problem as a monotone inclusion, you will design a preconditioning matrix, which is once again much more complex than the previous case, but the algorithm looks exactly the same. It's just a different operator and a different preconditioning matrix. And this is what the algorithm for generalized Nash equilibrium seeking would look like. You still have proximal best response dynamics, but there are extra dual terms. I will go fast on this, but the main idea is that this comes almost for free because of the operator theoretic interpretation. And some other extensions that are almost free for using the operator theoretic interpretation. Well, first of all, this update requires solving an optimization problem at each iteration. So what if you don't have time to solve it up to almost infinite precision? What if you have to stop at a certain point? Yeah, convergence still holds if the updates are inexact, and in particular if the error on the updates is summable. But this condition can actually be satisfied pretty easily, as I'll show in later. And also we have proposed some acceleration schemes, which basically correspond to applying an acceleration scheme to this operator written in compact form. And because we wrote our iteration just in this very simple form, the convergence proof of the acceleration comes almost for free. And finally, I also mentioned that one big limitation of these algorithms is that each agent has to keep an estimate of all the actions of all the other agents. So this means that the algorithms are not scalable because the overall estimate grows with the number of agents. So the state space grows with the number of agents. So these algorithms are not scalable. However, scalable solutions are known, and in particular, we developed some for the case of aggregative games where the cost function does not depend directly on the action of the others, but it depends on the action of the others only via aggregation function. And in that case, it's not needed for each agent to keep an estimate of the action of all the other agents, but just to keep an estimate of this aggregation value, whose size does not grow with n. Okay, I'll just show a couple numerical results before concluding. So I said about inexact updates. So what you can do to solve the optimization problem, the argmin in each iteration, is you use a projected gradient method for each one of these problems at each iteration. Actually, you can a priori impose that the error on the optimization decreases, and you have to have increasing precision because the error must be summable. However, since the iteration is converging, you can show that the number of gradient steps used to reach desired precision is not increasing. And in particular, this graph compares the number of gradient steps, total number of gradient steps performed by, sorry for not changing the legend, this is our method, PPP, and by a forward backward method. So it shows that not only our algorithm is faster in terms of iterations, but even considering the total computational time, forward backward algorithms are greatly overperformed. And the other one is to show that acceleration actually works in practice. And yeah, here we tried 3 different types of accelerations, and the number of iterations to convergence can be reduced up to a factor half. In conclusion, operator theory is a good tool to study Nash equilibrium seeking and generalized Nash equilibrium seeking even under partial decision information scenario. And we proposed a fast method, which is how it performs the pseudo-gradient method studied in the literature. And thanks to the operator theoretic interpretation, we are also able to easily give a number of extensions. This field is quite unripe, I think, the Nash equilibrium seeking and the partial decision information. some of the open challenges are relaxing the monotonicity and network assumptions. So, for example, some works were proposed to seek Nash equilibrium over directed graph or with less monotone games, not strongly monotone games. And we also did some work on directed communication graphs. And I think that the biggest problem remains scalability, although this is a solved problem for aggregated games. If you don't have any structure on the game, it might be quite difficult and even a fundamental problem to make probably convergent scalable algorithms. And that's it. Thank you very much. And I'll take questions if I have time and if there are any.
Thank you, Mattia, for this very, very interesting talk. Full of results, I should say. Is there someone that has some questions? Iko. Perhaps Marika? Yes. Also Elena. So Elena, wanna do a question?
Okay. Yes, Mattia. First of all, congratulations for your work. I really appreciate it.
Thank you.
Is there any effect of the topology of the network on the convergence rate in all the algorithms in general?
Yes, so when I showed the restricted monotonicity property of that augmented operator, wait. So the convergence rate depends on this parameter mu, which is the restricted monotonicity property of the parameter of this augmented operator FA, and FA contains the Laplacian.
Ah, the information on the network, okay.
So the worst case mu depends on the algebraic connectivity of the Laplacian.
Okay. And another question, any emergence is not required to know the cost function of the other agents, is it correct?
Yes, the cost functions are private, and I forgot to mention.
Therefore, each agent only know its own cost function, but not the others.
Each agent only knows its own cost function, and in the case of aggregated game, each agent only knows its own cost function and its own part of the coupling constraints. So each agent only knows AI, and it doesn't know AJ.
And another question, when you speak about aggregation, then in updating its information, its agent share what? The estimation of the aggregation made by the neighbors?
When I'm talking about aggregation, so each agent keeps an estimate sigma of the aggregation value, which is a function of the real actions, x minus I. Okay, and then they do the dynamic tracking, meaning that they do consensus on the estimate, but then the estimate I is updated as some part which depends on the consensus. And then they do gradient they do the tracking, which means they update it with, in the case, this is in the particular case where the aggregative function is the average of
all the agents. And what happens if, rather than considering all the agents, one consider only the neighbors? Is it possible
this was actually the first branch of Nash equilibrium seeking which was studied, and it's called full information scenario. So it's mathematically it's equivalent of assuming that you know the strategies of all the others. In practice, you can implement it in a distributed way, but it requires structure on the game and the communication network.
Okay, thank you.
Are there some other questions?
Thank you for your question.
So just to congratulate Mattia for this very interesting work.
Thank you.
Okay, I was wondering just a very quick question on the example you showed, for example, for traffic. Did you try to apply it to this kind of situation? What are the
I did not personally, but in our group there are two guys which are working more on applications, and in particular there was a guy who was Carlo Cenedese is working on mechanism incentives for traffic regulation and how to fill the valley and improve congestions. And his simulations results are pretty encouraging, although he's not working on partial information, so he assumes that there is a central coordinator.
Yes, I wanted to ask you which one of these formulations is in particular applied to this application.
I think that he was using the full information scenario, so where there are no estimates, but instead they also know about many works with aggregative games for control of the electric grid, where the aggregative value is the overall demand. So you want to know which algorithms?
Yes, I was. Yes, exactly. Which algorithm?
The algorithm for aggregative game is not shown here, but yeah, it's the one I was sketching to Professor De Santis.
I see. Thank you.
Thank you very much for your question.
So just a curiosity of mine, Mattia. So you showed us some possible applications. I would like to have somehow a flavor of how many agents can be considered and the time of computation. I mean, you have done some studies, no, some case studies. So I just want to have a rough idea of what we are talking about.
So this is a very simple case. It has 20 agents. And as you can see, the iterations to convert to a relatively good solution are already 10 to the power 4.
And okay, of course it depends on the computer where you do this kind of computations, but we are talking about how much? 1 hour, 2 hours?
Oh, no, not much. It takes some minutes.
Some minutes, okay.
It takes much more time for the gradient methods, which have require much more iterations. But this is the case for non-aggregative games, for which as I said, the algorithms are not scalable. So even 20 agents it starts being already a lot. But for the type of aggregative games, in particular, this other simulation was with aggregative games. It actually almost matches the case of a centralized controller. So it takes quite few iterations, and it is for 100 agents.
That's a very good result. So when you switch from a centralized architecture to a decentralized architecture, there are at least two reasons for doing this. First of all, the problem you are going to address, right? In the sense that there are situations in which there is an agent that, of course, that may not have information about the neighboring agents. So this is a problem that one should address. But what you are losing, passing from a centralized approach to a decentralized approach in terms of performance, time of computation, what else?
Well, you are losing in terms of number of iterations. That's yes. So if you have a centralized algorithm, probably you converge in faster. But if you consider only the computation faced by one agent, you can you can even have improvements with respect to a centralized controller, because here each agent is dealing with a smaller number of variables, so smaller dimensional problems. If you put everything in a centralized controller, you have only one problem, but much bigger.
Okay, thank you. Thank you very much for your answer. Are there some other questions, curiosities?
Thank you, Professor.
There is a hand raised.
Ah, really?
Yes, Laurent.
Laurent.
But actually, it's Alessio.
Ah, Alessio, indeed. With the name Laurent.
Yeah, because we are with Laurent in the same office, so we are watching together. So,
okay.
Thanks, Mattia, for the nice talk. Actually, would like to add something with respect to what Marika was asking. I would like to know if you can have an idea of the price of anarchy when you deal with aggregative games with respect to traffic applications in your mind, according to your opinion.
I mean, this is part of mechanism design, I guess, when you formulate an optimization problem as a Nash equilibrium. I have no idea. I know that for congestion games, it's bounded by a half, right? But no, I'm not studied this problem.
Okay.
I'm more focused on the solution of the Nash equilibrium when it's already in that form.
Okay. Okay. Thank you. Just a curiosity.
Okay. Are there some other questions from the
Giordano
audience?
Costanzo.
Ah, please, Costanzo. Yes, please go ahead.
Mattia, nice to see you again.
Long time no see, Professor Manes.
I'm very glad to listen to your presentation. And unfortunately, where I'm now, I'm not a good connection. I sure missed some part of your presentation. However, I have some curiosity about the alpha parameter in your PPP approach, because it seems to be both a parameter of in the functional, so it's a smoothing parameter, and also a step, the gradient step. Is it so? The role of alpha.
Which slides are you referring to? Maybe you have any idea?
Okay, it appears at the denominator of the regularization in the functional, but it seems also okay here in the damping factor, but it is also the step of the gradients the projected gradients. So that
I think that they call the step of the gradient tau. So this alpha comes from.
Okay.
This alpha comes from here. I mean, there might be some typo. The alpha comes from here.
Okay. Oh, no, there was a table where you compare the tau with the alpha. So
yeah, okay.
Where is the table? So you consider the case of tau that was going to 0 for the
so this
forward
means that in the forward backward you have two steps. You have alpha, which is independent of n, and it's actually the same. And then you have tau that goes to 0. And in our algorithm, we only have alpha.
So my question is the step size is unique for all the agents. So it's something that is known a priori by all agents. This is shared by all agents, or
yes, this can actually be relaxed, but yeah, it's a common step size.
Okay, so it's a fixed step gradient that you apply.
Yes.
So it's not the most efficient one when you speak about gradients.
Well, since it's not an optimization problem, you don't have really efficient like mixture of accelerations. Or, you have to solve a variation inequality, so you do have some accelerations, but if you use that. What were you referring to? Talking about
no. When I use the gradient method to my something, I quite use line search to determine the best step at each step k. So tau normally is not a constant step in gradient methods, but it's variable step methods, right?
Yes.
Now in this approach, you have to fix a priori a single tau for all agents, and then to keep this to stick to this tau for during all the algorithm, right?
This is a very interesting question. Actually, line search will be preferable, but I'm not sure. I mean, you cannot implement it in a distributed way.
So parameter that must be determined a priori, right? Once for all.
I mean, you have other results where the tau diminishes, so it's going to 0, and you can even have uncoordinated step sizes, so one step size for each agent. But I mean, line search is not an option at the moment.
Very good. Thank you again, Mattia. Very nice presentation.
Good to see you.
Okay. Are there some other questions for Mattia? It seems not. Okay, so thanks again, Mattia, for being with us today at the JUS Colloquia.
Thank you very much, Professor Pola.
Let's hope to see each other somewhere in the world in some conferences, right? Hope so.
Let's hope so.
I see you also, Elena. Okay. So if there are no more questions or comments, I wish to all of you a good day. I see also Marika here. That is muted.
Oh, I wanted to say, of course, thank you again, and I hope to see you all in the next conference, the next opportunity. But also in L'Aquila, Mattia, if you come.
Really, it would be great.
Are you there for Easter?
You will be there here for Easter. Here, I mean, in L'Aquila for Easter.
I'll be in Italy for Easter, so maybe.
Oh.
Otherwise, next conference might be Cancun.
Yes.
CDC. Yes.
Let's hope so then.
Okay. Very good.
Very, very good. So let's thanks again the speaker, and I wish you all a good day then. Goodbye.
Thank you to everybody.
Thank you.
Thanks again.
Bye-bye.
Bye.
Bye.